All right, so for the last couple lectures, we've been learning about how we can learn information about stars by analyzing their starlight. And we've talked about looking at their chemical composition, their color, by analyzing different kinds of spectra. I want to move to another thing that we could uncover about stars, and that's how they move. And to do that, I need to teach you a new way that we analyze starlight, and that's the Doppler effect. So again, we've been looking at these two different kinds of representations of stars' light, the idea of an absorption, dark line absorption spectrum, and this idea of a black body curve. And we've been talking about how the dark lines in this spectrum, or the dips in this curve, tell us about whether or not the star has helium in it or hydrogen, its chemical composition. And the peak in this black body curve, where the highest point happens in terms of its wavelength, tells about the color of the star, and it tells us about the temperature of the star. So I want to talk about how we're going to use these ideas of the dips or the dark lines to learn about the motion of the star. So again, just to review, peak in the black body curve tells you about the temperature of the star and its color, and the pattern of lines that appear as either dips in the light curve or dark lines in the absorption spectrum tell you what the star is made out of. And so I'm just going to tell you right now that to know whether the star is moving, we look at those dark lines in the absorption spectrum or where the dips are happening in that light curve. And if they've been shifted in terms of the wavelength that those dark lines occur at, from where they normally would be for a star at rest, then we can find out whether the star is moving or not. And so I'll talk to you more about that. So the definition of the Doppler shift is the change in wavelength of light due to the relative motion between an observer and an object that's moving. So it's the relative motion between the thing giving off the light and the person observing the light. And when that object that's giving off the light is moving, there'll be a change in the wavelength and the pattern of lines in its spectrum. The first one that's commonly seen in textbooks uses this idea that what if you had an object that was giving off light that was originally positioned at position 1, and then later at position 2, and then later at position 3, and then 4. And at each of those locations it gave off some light that's represented by the ring of energy that's moving outward. So by the time the source had moved to position 4, that information had moved outward. And so you can imagine a wave of energy leaving this location, moving towards this observer. So this is the light given off by the source that's moving towards this observer, and this is the light given off by the source that's moving towards this observer, while the source itself is traveling that way. So for the observer over here, the source of light is moving towards or away?
Towards.
Okay, good. And for this observer?
Away.
And you see that the wavelength of light that this observer receives, is that a long wavelength of light or a short wavelength of light? Long. And for the one that the source is moving towards?
Short.
That's kind of the whole thing right there, okay? So the idea is when the source of light is moving towards an observer, the light that you'll receive is compressed to shorter wavelengths, and when the light source is moving away from a receiver, the light that you receive is at longer wavelengths. And so we'll kind of talk about that more and more. So I want to unpack this definition. Change in wavelength of the light due to the relative motion. So what if you had a source of light like a star that's not moving, its velocity 0, and it gives off some particular wavelength of light. If instead that source of light, that star, were moving, but now it was moving away from the observer. So here's our observer, there's your source of light, it's moving away. If I were to show you the source of light now and draw it as another wave, would I draw it with a longer or a shorter wavelength? Longer. Okay, good. And if I instead go to the case of the light moving towards, I get a shorter wavelength. So that's the idea of towards and away and long and short wavelength. And I'm going to keep trying to color code things in blue and red for a very particular reason. So you'll notice that I made the word away red, I made the arrow red. That's because when we talk about light, which has the longer wavelength, red or blue light? Red light. So you'll see me coding things for away and longer wavelength with red colors also. Don't think that means it's the color of the object. I'm just trying to kind of cue you to long wavelength as a way of thinking. So we call something redshifted, or it's the light from an object redshifted, whenever that object's moving away from the source. So that was the case that we looked at where you have a star moving away, the light has been shifted to a longer wavelength, and we call that redshifted. Moving towards the light is shifted to a longer wavelength, or redshifted. The opposite happens when the object moves towards you. The light that we receive as an observer is blue shifted, or it's shifted to a shorter wavelength. So this only works if the motion of the object you're looking at is along your line of sight. So if an object's moving toward or away from you. So right now, if I were that source of light and you guys are the receiver receiving all the light on Earth, and I'm moving towards you, the light you'll receive from me will be shifted towards the long or shorter wavelengths.
Shorter.
Okay, and we would call that red or blue shifted.
Blue shifted.
And right now I'm moving,
Away.
my light is shifted to longer or shorter.
Longer.
And my light would be called
Red shifted.
red shifted. Perfect. So if I'm moving like this relative to your line of sight, back side to side, I'm not moving toward or away from you. My light is not Doppler shifted at all. So the long line of sight really matters. So sort of as a visual way of looking at that, you can say that if the motion of the star is up and down or perpendicular to the line of sight, if its motion is perpendicular to your line of sight, there is no Doppler shift. You can't detect that motion. It's only whether it's towards or away. Okay, so now we need to get into some representations that look more like what we see from stars. I'm showing these kind of, waves of light coming out, but that's not what we actually kind of tend to analyze when we look at light from stars. So there's two things there's one more thing that I need to add to this. So you have blue shift shifting to longer wavelengths, red shift shifting to longer wavelengths for motion that's away, and blue shift shifting to shorter wavelengths for motions that's towards. And this is sort of the mathematical representation that lets you know how all of that would work functionally. You'd get a change in wavelength for one type of velocity or another. But the other thing that I need you to realize is the amount that the light is shifted, the amount that the lines will be shifted towards a long or short, is exactly proportional to how fast the object's going. So faster motion, greater amount of shift. No motion, no shift. Faster motion, greater amount of shift. So I want to move to those other representations. So I've been drawing this application, but we don't see wiggles of light coming into us. We get a full spectrum of light with dark lines in it from stars that look more like this, an absorption line spectrum. And I was saying earlier that it's the lines in the spectrum that will be shifted when an object is moving toward or away. So if I had a star instead that was moving away, and I was to look at its spectrum here, and these were the lines of that star when it wasn't moving, I want you to just think about it for a second, and don't talk to your neighbor, but on 3 I'm going to ask you to point. Which direction would the lines in that spectrum be shifted if the motion of the star is away? I want you to think about that. Okay, let's point on 3. 1, 2, 3. Oh, yeah, good. Towards the red. Good. Okay. And if it's a star that is moving towards you, its light will be blue shifted, and the lines will be shifted towards the blue. Now, I want you to talk to your neighbors. Go ahead and talk to each other for just a second about this. Which of these two stars is moving faster? Which of these two stars is moving faster?
So if it's faster, that means it's motion, right?
Yeah.
Yeah, so then the middle one is shifted one?
Yeah.
Okay.
Okay, let's check in. So is it the star that is red shifted or the star that is blue, whose light is red shifted or whose light is blue shifted that's moving faster?
Red shifted.
Red shifted, okay, good. And it's shifted by a much greater amount towards the long wavelengths than this is shifted towards the short wavelengths. Okay, excellent. Those are all the main ideas that I wanted to make sure we covered. First, Doppler shift doesn't tell you about color. It's the peak in the light curve that tells you about color. Doppler shift doesn't tell you about chemical composition. Which pattern of lines or dips appear in the spectrum of stars tells you about chemical composition. To understand if the star is moving, you look to whether or not the light has been Doppler shifted towards the blue or the red. So for the next activity that we're going to do, you're going to be asked to make representations of different kinds of stars' light using these ideas of dips or lines in the spectrum and whether or not they're shifted for information that we give you. So you'll need to get your whiteboards, and this will be the activity for today for the whiteboard activity.